Welcome to Study Loop.
Taking a look at nuclear energy again. So in the first part, we have the pi is P over D equation, where D is 2R, and pi is P over 2R, R is P over 2 pi. Substitute 1400 M for P and 22 over 7 for pi. We get R equals to 2.8 meters, where they're calculating the inner radius, where R in equals R out. Subtract R. R in is 220.8 meters. Calculate the area of the diameter, where A diameter is equal to A out, take away A in, where the area of the diameter is 2788.3 meters squared. Then we can calculate the volume of diameter. That is A diameter multiplied by H diameter, which is the height of the diameter. B dam is 836.49 meters cubed. So we can calculate that molar heat transfer. That is Q hat brine. That is negative Q hat brine, negative 1.131 kilojoules per mole. So now we'll look at Q hat freezing. That is negative 8.19 kilojoules per mole. The time is 5.184 times 10 to the 6 seconds. So the average cooling rate is equal to 7,326 kilowatts. Following this, the brine flow rate is 6,996 liters per minute, and the power used is 1800 kilowatts. So once the water in the well is frozen, the only cooling requirement is to counteract the environmental heat loss, which was assumed to be negligible in the calculations that we've looked at already. So therefore it is expected that less power will be used once the dam has been formed. So the initial nuclear accident has released several radioactive species. So out of those radioactive species, cesium-137 has a half-life of 30 years, and it is approximated that it will remain in the environment for several decades. Iodine-131, cesium-134, and cesium-137 are primary radioactive species. So at elevated temperatures, the zirconium is in the control rod to react with water and form zirconium oxide and freezes hydrogen gas. So these conditions exist due to the cooling water leaks, which both can raise the temperature and put metal in close contact with water.